So without any further delay, let me welcome back Alok.
Okay, so let me just very quickly recall what we did last time. So just to sort of draw it pictorially, we are looking at a generic scattering process of objects with momenta, and there can be other, as we discussed, multiple moments. And then we scatter into bunch of Godwin, is this visible or is it, should I write thick, more thick? Oh, and bigger. Okay. And of course, during this process, it will emit gravitational radiation, as we discussed, and the radiative field that we call in the frequency domain that we call. And this is what we want to compute. So just to remind you that in d dimensions, this is the coefficient of 1 by r to the d minus 2 by 2. And then I ended at some point that if you just do the usual Green's function analysis, then you can show that this quantity can be written as some normalization factor times integral over entire space time. And this is the full stress tensor, just want to remind you, which includes stress tensor of all the matter, all the objects, and the stress tensor of gravitational field also. So the whole thing. There is a small technical caveat that I had not mentioned yesterday, so let me just mention now that. So remember the way we got it, if you remember, we had to take in our integral to begin with, when we set up, there was a mod, there was some object which was the retarded Green's function. And then we are taking the limit where mod x minus x prime is approximately equal to mod x, because we are taking the x, the distance of the directed to be very large from the origin. But of course, there is a caveat here, because here we are integrating over all the entire space-time. So obviously this is a little naive, because if you are integrating over all space-time, there are x prime points which are very close to x. So this has to be taken, done little suitably. But for the purpose of this lecture, it just means that we have to adjust some boundary terms at infinity. So I'll just write it like this. So in general, we can get some, we have to be careful about what happens when x prime also goes to infinity, and that we have to adjust those terms, okay, because we are taking mod x to infinity. So, so that's really the expression. And I think in one of the tutorials, this was derived yesterday, or it would be derived. Yeah, the expression, this will be derived in one of the tutorials. Okay, so this is where we are starting, and remember, we want to do a small omega expansion. So we want to now do a small omega expansion. And prove the soft theorem that we wrote yesterday. Okay, any questions about basically this is where we stop, but any questions about this last lecture? Okay, so now let's start proving this. So let's, the first thing we should do is to, this is the setup that we are going to use. So we say that, okay, particles came, the objects came from far apart, and there is some, let's choose a completely arbitrary region. So let me redraw this picture here. So the objects are coming from far apart at t equal to minus infinity. And we assume we take a sphere of radius L. I'm just going to draw it but this is the time direction. So like I'll draw it like a cylinder. So there is some domain of spatial size L. And this, right now this L is completely arbitrary. So what we are, the way we are going to solve this problem, we want to evaluate this integral in the small omega limit. And the way we are going to do it is to say that, well, let's take a domain L. L should be very large as you want, such that outside of this mod x prime equal to L, particles are approximately free. So, and inside, we have no idea what is happening. Okay, so is this clear? So we are using the assumption one that we said yesterday. So for mod x prime greater than L, particles, I mean, they're never obviously completely free because there's always gravity. So we will quantify this a little more, approximately. Free. But in such a way that if you take L2 larger and larger, they become freer and freer. That was our crucial assumption. And inside for mod x prime less than L, we have no clue. Okay, is this setup clear? And of course, in the end, the answer should not depend on L because L is just our completely arbitrary choice to solve the problem. So in the end, it's just some domain we are choosing. And in the end, the idea is to take L as large as you wish, okay, so that this assumption is satisfied. Is this clear? Okay. So let's first solve the integral in the outer domain. Okay. So we are going to split this. We will split it in two parts, and we will call it greater and okay, by greater we mean that we just integrate for all mod x prime where the spatial radius is larger than L, and the other one is this one. Is this clear? Okay, so let's first do this one because this one is easier because we are assuming that particles are almost free. And so now these objects are almost free. And so now we know that if they were free, then outside of in the outer domain, the stress tensor of the system is going to be equal to n plus m. So I'm writing all the objects as we saw as point particle with multiple moments. Each one have their own proper time, and then we will go from minus infinity to. Now I'm going to here write for now mod x prime equal to L, but of course I will tell you exactly what it means in a minute. And as I said yesterday, for this example, we will assume particle have no other multiple moment. It only has linear mass. So that means that the stress tensor is A sigma A. Is this clear what I have written? Any question about this? So of course, in general, it can have other multiple moments. For just for explanation, I am suppressing it now, and I will give you the exact result in the end if you assume that all other multiple moments are switched on. But the analysis we do here, that's the essence of the analysis. So the thing that if you add the spin angular momentum, the steps don't really change. You just have to do a little more calculation. Conceptually, nothing changes. So that's why I'm just restricting to this this case. And now we have to quantify what this object is. Okay. So now let's draw the spatial slice, not draw things in space-time. So this is my mod x prime equal to L. And let's say that all the particles that are coming in, let us say that all the proper times are such that they all start at sigma A equal to minus tau A. And the proper time is such that whenever they hit the boundary of this domain, it's always sigma A equal to 0. Now you may think that, okay, this is true for incoming particles, but what about outgoing particles? Because where this tau is effectively infinity. So that we are saying that the particles come from minus infinity, the incoming objects come from minus infinity, and they hit this domain at the proper time equal to 0. What about the particles which are outgoing? Now, naively, we would say that, well, we should do it like, we should take here, let's say some sigma B as some tau B, and such that these particles are exiting at this domain at sigma B equal to 0. But you could just say that, I mean, if I give you a free trajectory, let's say some random trajectory like this. So Godwin, if it gets shrink, you tell me. Then I can always choose sigma a to go to minus infinity for all the particles by assuming that for outgoing particles, my velocities are incoming. Is this part clear? I can always assume that all my even for outgoing particles, all my momenta are negative, but tau a is always going to minus infinity. Is it clear? So that means that I can always choose this V such that all tau a go to, we should understand they are all going to minus infinity. But now with the caveat that outgoing particles have negative momenta. Is this fine? Okay, this is just a convention. You can put it to be tau b also. It just helps us democratize everything. Otherwise, we have to write some of them from, up to 0, some of them from minus infinity to 0, minus or plus infinity to 0. So we don't want to do that. We want to keep this sum as one sum. That's why we are choosing this convention, so that it's easy to write the stress tensor. So with this convention, then T mu nu x prime, I mean, it's just exactly this, except now this point becomes 0 for all sigma a. Is this clear? Now this is true if the particles are, this is just a stress tensor of the particles. So we have not really included the stress tensor of the gravitational field, right? So in the end, we should also include okay. I will tell you exactly how to deal with this now. For now, we are going to focus only on the contribution of the objects, and then, but we should keep this separately. So is this part clear? Because this is quite important. That this T mu nu really is, it has contribution of the stress tensor of the gravitational field also, which is between these particles floating. So that part I'm not writing down here. I'm just writing it schematically like this, and all the object stress tensor is this one. Okay. Now, so if the assumption is telling us that, well, we can treat these particles as free if we go to early or late times, which means that I can simply rewrite this, I can substitute that object there, and I can write omega x hat as this normalization times I'm just substituting all the entire stress tensor for the particle. D sigma A. But now if they are free, then this is just right. If they're free, then they're moving with uniform velocity. So the P and V come out of the integral, and you just get this object. So this is this plus H tilde mu nu 0 nonlinear omega. So the contribution coming from the gravity stress tensor, I'm calling it H tilde mu nu nonlinear, because that includes the H itself. That's a nonlinear contribution. So that I'm just going to write it like this, but we are focusing explicitly on this object. So now let's do this integral and see what we find in the small omega expansion. So that's not a, but that's now not a hard integral, because we have, so let me just rewrite this one. So we get then we have integral or A sigma A. Is this clear? Yeah. So of course, this is telling us that I can replace x prime with xa sigma A, right? And because we are always only focusing on the trajectory outside, and we are also integrating outside. So that means that we can always replace x prime with xa sigma A. Is it clear? Because both arguments are in the same domain. So so that means that this integral simplifies, and we get, oh, there should be n normalization. And we will get something very simple. And integral 0 d sigma A e to the I k dot xa sigma A. Right? Please ask if there is something is not clear. Okay, so now it's simple because we are assuming particles are free. So we know what this trajectory is. And this trajectory is just inertial particles trajectory. So we can substitute and solve it, solve this integral. That gives us the contribution of the outer domain. And so you see that the you just while skip one step, but of course you notice that if this trajectory which is free is of the form some displacement plus. And now we have an operational meaning of what this C is. That's the location where the particle hits the outer boundary of the domain. Because at sigma A equal to 0 is where every particle is entering the domain. And at sigma equal to 0, the location is precisely the C. So operationally, C is the position where any part, CA is a position where every particle is entering our domain of radius L. Right? And so now we just substitute it here, and this integral, as you know, you can do, and you will find, so this, and of course, there is this H tilde mu nu nonlinear. And so then the H tilde, so the final answer, the particle contribution from the outer domain. So, rather than writing nonlinear every time, I'm just going to write this, the particle contribution is precisely 1 to n plus m A oh, sorry. Right? Is this clear? Because the e to the I k dot ca comes out of the sigma integral, and the integral is from minus infinity to 0, and so that gives us just this factor. Okay. Now notice that we want to. So far we have not done any expansion in omega. We have just evaluated the contribution of the particle in the outer domain, assuming the domain is so large, particles are effectively free. But if you do expansion in omega, remember k mu vector was simply omega 1 x hat. So expansion in omega is you have to expand this guy. So it gives us so when you do the expansion, and we are going up to order omega to the 0. So remember, you see the first term is exactly the leading soft factor that we wrote yesterday. But this is V, so I can replace both by P because we prefer momentum more than velocities. Divided by PA dot K. But the next term then, because we want to go to one more order, and then the next term is of course expanding the exponent, and that would give us, oh, there is an I here, sorry, minus I here. And the next term will be plus n. Yeah, I can keep n here. So no, it's fine. So plus the next term will be I will cancel and k dot ca come out, so we get with a minus, I guess. And then you have a PMP, P mu A. Okay, so this is the entire particle contribution to the outer domain up to order plus order omega terms. So up to order omega to the 0, this is the contribution. Okay, now we have to do the other contribution, which looks impossible to do because we have no idea what is happening here. And so how do we contribute? The real object is to compute the contribution from the inner domain. This was trivial. I mean, we just assume the particles are free. But if you, and I will come back to this assumption after finishing this proof, because that is where Ashok will enter tomorrow, where this assumption breaks down. Okay, so now we, again, just to say that we are right now only focusing on the particle contribution. There is always this field contribution, the gravitational field contribution. So now let me compute the contribution from the inner domain, but again, only the particle contribution, let's say. No, here I'm going to just not, right now, not just do it the way we did it. So I just write it. And that's, then we have, sorry, I'm just writing the same thing again. Except now I don't know what is T mu nu. So here actually I cannot do, sorry, particle contribution to begin with because I can't separate the particle and the gravity contribution. So here I have no idea. This T is the total. Okay, so it looks impossible task, but again, the fact that we want to expand it to order, do a soft expansion, it would really help us, as we will see in a minute. So the obvious thing to do is to remember that something that we noticed yesterday, that even in the full theory, this T is such that it satisfies local energy momentum conservation. Right, just from the way it was written, I mean, just trivially. That means that if I want to evaluate, so let's do the following trick. Let's say I evaluate this quantity. This quantity then is, I'm just contracting both sides with k mu, but contracting this side with k mu is same as doing is this clear? Just nothing, a cheap trick. Now if you can integrate by parts, but if you integrate by parts, when this hits this guy, it is 0 because of the local stress tensor conservation. So the only term that survives is the term that comes from the boundary term. So that means the only term we get is prime mu and there's an I here. Is this clear? So it's just our, what is it called, Stokes theorem, that just write it in a boundary term, where n prime mu is of course the radial vector at this location of the sphere. Okay? So we just use the Stokes theorem and rewrite it in this form. And this form is interesting because now the entire contribution has been reduced to the contribution on the boundary of the domain. But this boundary is as large as we want. So again, we can always say that the particles are free at the boundary because L is as large as we want. So then this has a, now we can try to evaluate this contribution. The only subtlety now is that it's an integral over just the cylinder of dimension d minus 1 and not the full space time. Okay, so let's do, is this clear what we did? But this is an extremely important point. We are not getting this h mu nu. What we are getting is actually contraction of h mu nu with k mu. Our object is to get h mu nu. And so we will see how far we can go. So once again, the fact that we are only looking at the, we are now we can look at, now because we are at the boundary of the domain, and this domain is very large, we can now separate into the particle and the field contribution again. So now I can focus on the particle contribution. And that is same as, and we can write it like this. So instead of writing the integral over this cylinder, we just write it as integral over whole space-time, but localized on the with the delta function, and then we have everything else remain the same. Now I'll skip some steps and well, okay, let me write one more step. Did I miss some? Yeah. Well, by now I must have missed many minus i's, but let's not worry about it. Yeah. I'm happy Ashok is not in the audience. So then this is this times delta D. Is this clear now what we have done? Because we just reduced the problem to the far away domain. And then we just, then the particles are again by our assumptions free. And so we can substitute the same stress tensor we used for the outer domain contribution and accept that there is this extra delta function. Because the particles are free, we know that x prime mu sigma A is same, xa sigma A, again, just rewriting what we wrote earlier, is Ca plus sigma A. But the trajectory is localized at mod x prime equal to L, and all the particles, as we saw by convention, are exiting or entering the domain at sigma equal to 0, the proper times equal to 0, which means that at this location, your because of this delta function, really we are going to evaluate the things as at sigma equal to 0, which is CL. This is just an observation right now. I have not used it, just to remind you that we know where in terms of the parameters that we are describing, we know where the particles are entering and exiting because of our choice of proper time. And now, okay, there are some steps that I'm going to skip in the interest of time, but let me just tell you what exactly we have to do. So first, we of course again solve this delta function. So that I hope it's okay if I just not write and just do it. So we remove this guy, we remove the integral, we put the integral d sigma A here, all the other integral I'm going to put outside. Integral d sigma A. Now this d sigma I am not going from minus infinity to 0 or anything. It's over the entire thing, except it's localized at this location. Right? That's what this delta function is doing. And then we have xa sigma A free. And outside this integral, we have the same object that we had earlier, which was PA mu. And I just want to recall that this guy is contracted with this normal vector. And this x prime, of course, then it becomes mod xa sigma A minus L. Is this clear what I did? I just skipped one step of integrating over x prime and then substitute x prime equal to xa sigma A, so we get that object. And now I'll just skip one step because this delta function we know how to solve, right? Because we know this. When Oops, what did I write? Xa sigma is not 0, Xa sigma is L. When Xa mu sigma A at sigma A equal to 0 is L. Sorry. So this is what the delta function is solving. But this delta function, you know, by Jacobian rule, if you have delta of f of x, you have to do 1 over mod f prime x, etc., etc. So if you do this, in the end, you find that this is going to give you simply, so I'm skipping just one step of this delta function. When you do this, you just get yes. Yes. That is L because, I mean, oops, mod. Thank you. Sorry. Because we are saying that it's entering the domain at sigma equal to 0. So the radius of the position of the particle at sigma equal to 0 is always exactly equal to this L. Thank you. Yeah. No, it's not. It's there. We are now only because of the fact that we got this expression where the whole inner contribution got localized onto the sphere, and we can take the sphere to be as large as possible. Again, we can split it into some field contribution and particle contribution because particles are almost free, and so you have some. So right now I'm only focusing on the particle contribution. So inside, I would not know what is happening. I have no control. I don't even know. But because of the fact that this total T satisfies energy conservation, so I had to use total T, which is why I could reduce it to this. But once I've reduced to this, now I can split it into the particle part and some field part. So I'm not ignoring the field part. It's just I'm just not writing it right now. And then we have we get. So it will just give us, sorry? Yeah, I'm skipping that step because of lack of time, but when you do it, I'm just writing the final result. And this is equal to not, this is not equal to new, because I free index is new. And divided by, no, that's a good point. It should be divided by, yeah, that's a very good point. I should get, sorry, just give me 1 second. Sorry. It's going to give me, I apologize. CA mu, CA nu times K nu. Divided by P dot K. Thank you. Yes, you are right. So now if I do expansion up to order omega to the 0, I can forget this term, right? Because of the fact that this is already order omega to the 0. There is no order 1 by omega term. So that means that up to the order we want, it is exactly this plus order omega. Is this fine? I may have missed some minus plus signs, which are actually important when we combine both, but I'm just giving you the sketch of the derivation. So, you can just look at all the factors correctly. And now it turns out that if you add both this contribution, the out and the inner contribution, but before that, we have to know what is h mu nu for the inner domain. We don't have it yet because we have this, contraction with the K. And now here is a key point. So you see that, so I'm going to write something and please ask me if it's not clear. So inside mod x prime less than or equal to L, if you do the Fourier transform, then this is analytic in omega or k. Is clear what I mean by this statement? That when you expand h mu nu, and if you are getting h mu nu contribution only from the stress tensor which is inside, then if you expand h mu nu, there can be no pole in h mu nu, because of the fact that to get the pole in h mu nu, you should have the contribution from the as far away from the center as possible. So the fact that all the contribution we are getting coming from the inside, whatever gravitational radiation we get, it cannot have any soft factor. Right? You see why this is obvious from the previous computation, because we got the 1 by k term, 1 by omega term from the most free part of the trajectory, right? Which is where particles are far outside. So if your particles are inside, it can never give you a 1 by omega term, which means that your h mu nu is always power series in k with no negative powers of k, right? Which means that it tells you that any h mu nu. So given this data, I want to solve for h mu nu. That's my goal. So what is my h mu nu? The h mu nu would be less particle. So I'm going to now write the answer, then we will argue based on this why this is correct. So this is equal to minus in T a mu plus any term which has the form a mu k nu minus eta mu nu a square times some arbitrary function of a and x hat. So why am I saying this? I'm saying that given any h whose contraction with k is equal to this object, and the fact that h has a power series expansion in k, the whatever ambiguity we are left with has to have this form. Because you see, if I contract this with k, it goes to 0. Right? So this is this part I am not able to determine. This function I am not able to determine. But notice the power of omega in this. It is omega order omega square. Is this clear what I have written? So it is absolutely true that whatever we do, the omega square terms cannot be determined by this in this theorem. Is this part clear? No, because it's analytic. So it cannot have. So whatever we do, we cannot determine this part of the radiative data. So this still leaves open what happens at order omega. So I will come to that in a minute. But this is absolutely telling us that order omega square terms are higher, we cannot determine from this theorem. Because to determine it, we have to know this function. And this function means we have to then actually solve the dynamics. Like we have to actually look at the process and then evaluate h mu nu as a as a solution to equations of motion. Is this part clear? So this is also telling us why soft theorems are non-trivial, because it's not like you can go to any order in omega and this kind of relatively easy theorem can tell you what h mu nu is. This shows the limitation that you can only go up to some order. So obstruction that we cannot get. So remember that we call the 1 by k term leading, omega to the 0 term sub-leading, and then this term would be sub leading. And the sub leading or high terms cannot be determined by this analysis. Okay. It still leaves open, can we say anything about sub leading? That I will come to if I have time later, but this certainly tells us that there is an obstruction omega square and higher order. So, which is also what shows non-triviality of our result, that it's not that we get everything for free, because at some point we have to solve equations of motion. Just the stress tensor conservation, which is just statement of gauge invariance, cannot be enough to give us radiation, right? So now we can just add these two contributions for the particle, and the final answer is exactly what we got. Let me just rewrite it. Yeah. No, so H, I know contraction of K with H. I know H is analytic. So now I want to know what from just k mu h mu nu, can I write down h mu nu? Now k mu h mu nu was this thing contracted with k mu. So this is an obvious piece. But there can be extra. What are the extra terms which are 0 when you contract with k? Anything that we have missed is the term which is 0 when you contract with k. And so obviously it should have this form. Is this okay? Yeah. So the tensor structure of whatever we have missed have to be this. Of course, there can be the actual stuff is in this f, which is some scalar function. But this is already telling us this, and this is already telling us that we can't, if we wanted to get radiation at this order, we are done. We cannot do. These theorems cannot tell us. We actually have to solve the equation. So now anyway, so if we combine all this, then we can just write down the particle contribution. Now remember that in this case, I assume the particles have no spin. So that's why we had the stress tensor has no sigma component that we discussed in detail yesterday. And then this turns out to be just equal to, please don't trust any of my factors. But, I'll write tilde here because we may have missed some factors of I, etc. I think there should be a relative I between them, which I think we got somehow because this had a 1 by I, the other thing I cancelled, if you remember. So up to sine, there is some relative factor of I, which I will put here. And I'm not writing all the steps, but if you just combine and look at the algebra, you can show that this is just true, that the answer, this is of the form. Where J A nu lambda is actually nothing but C A nu P A lambda minus C A lambda, which is really the orbital angular momentum of the eighth particle measured asymptotically for the free particle. So if you combine the less and the greater contribution, this part was obvious. This only came from the outer. But the outer also has one extra contribution, and that combined with the inner contribution, you can rewrite it in this form. Okay, so that's the particle contribution to the. That's a partial proof of the soft theorem we wrote down because it tells us that all the soft radiative field contribution coming from particle has exactly the form that we wrote yesterday. Right? Yeah. Oh, sorry. Why did I do that? I apologize. I'm spacing out. No, this is exact. No, so it's h mu nu. Yeah. Thank you. Yes. Yes. Which term in the? Yeah. Sorry, because I was just repeating. You're right. Absolutely. With the PA dot. No, that cancels because that term cancels. You just get this because order omega to the 0. It's just this term. Yeah. You see, because exactly because if you put this here, then in one case P will contract with lambda. That PA dot K will cancel. That will precisely give me PA mu CA nu. Yeah, and then the other one is the other one. So that's because the contribution from the outer domain had a PA dot K, if you remember. It was K dot CA, PA nu by PA dot K. Right? Which is exactly the term where this C lambda contracts with this. That's the term coming from the inner domain, and this is coming from the outer domain. I may have missed some signs. Signs are important, otherwise minus will not come. But the rough structure is this. Okay, now I will write, but we have not so far done the field contribution. But before that, let me now tell you we have again and again repeated this assumption that particles are asymptotically free, and let's test that assumption and what it implies. Yes. No. So C is exactly. So C is the location. C is if particles are coming from infinity, and with respect to some origin, the trajectory of the particle is C plus v tau. we choose one origin in space-time, and then the particle's trajectory is Ca mu plus Va mu tau. Yeah, but that's the choice of proper time, right? But I'm saying that this is just our usual free trajectory of a particle, which is basically telling us that Ca is the location particle occupies at tau equal to 0. No, I'm saying if you take a free particle trajectory, C is the, I'm just saying that if I just give you this, it's a parameter of the particle that we have to prescribe, right? Like the initial velocity. So this is the initial velocity, and this is the position particle will take at proper time equal to 0. Right? That's the specification. But you make an excellent point that if you measure particles' energy, angular momentum, and linear momentum, then we can read off these parameters of the particle. So these are physical parameters. Right? Because if you measure, of course, if you measure momentum and you know the mass, then you know this. But then if you measure orbital angular momentum, then you can, because you know P, you can deduce C. So, having C is same as having the orbital. Is it clear? Is it okay? The L, sorry, say that again. You mean the first term? Yeah. Choice of L. Exactly. When you added it, the final answer has no sign of, it is completely discrete from the parameter of the particle. So L went away, no? Yeah. Because of course we added, we added things for outside L, inside L. And so then L was just complete fake. It is just to regulate the domain outside which we are assuming particles are free, but it could be anything. Is this clear? Because that's an important point also. It's like we just introduce some regulator for convenience, but in the end the answer, of course, independent of choice of this L. Yeah. Yeah. So it left open the question of what happens at linear or omega, and I will tell you what happens in a minute. But what it's telling you for sure is that if you go to omega square or higher order, you cannot determine H from any of this analysis. And now you can, because you are asking, let me just say, now you can ask, okay, so it leaves open a gap. What happens at order omega? And actually the answer is the following, that if you pursue this at order omega, this analysis, I will not, of course, give you detail, then it turns out that, so at order omega, you can actually pursue this analysis. Harder to do, but you can do it. And then it turns out that this object indeed has an expression like this, except one caveat. It's of the form So let me explain the result. So we did the analysis only up to order omega to the 0, and we got this answer. And this answer is, of course, you can imagine that once we accept the assumption that particles are asymptotically free, it's a universal answer. In the sense, it doesn't matter if the theory is GR or any other theory. It doesn't even matter if the theory has any other multiple moments except mass and angular momentum. The result is completely described by this data, only this data. If you go to next order, which we did not go, but you can go, and it turns out that indeed the analyticity argument left open a gap. What happens at omega? And at omega, we can actually determine, we can follow this theorem, except there is one caveat, that if you are in GR with no other, not modified theory or something, then the answer would be precisely this term. So you can see that this term is order omega, because there are 2 k's in the numerator and 1 k in the denominator. And it depends only on the angular momentum of the particle. But if a theory is that scalar tensor theory is other theory, then there can be an extra term but that extra term depends on whatever is the coupling of the gravity is with the other fields, which I am just describing like this, and there is some k. So if it depends on, just as a slide, it depends on the 3-point coupling of sorry, I'm using now slightly this terminology of quantum field theory, but when I say graviton, it just means linearized gravity, graviton with other fields. If you have some other 3-point couplings, then that can modify, that can give you a new contribution. But if you are in GR, for example, then it will be just given by this term. Okay. So omega guy sits in between these results and omega square terms, which cannot be determined. So omega to the 0 terms are truly universal, whereas order omega term is, you could say, quasi-universal, in the sense we can write it, but it depends on some extra data of the Lagrangian that you start with. Is this part clear? Okay. Yeah, not for every theory it will be, you have to check what this is. So for R square, it may even vanish, so we don't know. But I can give you one concrete example. If you take a theory which has a term, extra term in the Lagrangian, which is, let's say, some scalar, let's say some dilaton with r mu nu alpha beta, r mu nu alpha beta. So if you add this type of term, then it will give you a non-trivial B. Okay, that's the yeah. But anyway, it's a slightly different discussion. But yeah, we will focus up to things which are completely under our control, which is up to subleading order. Now let me just go back and quickly tell you what this assumption implied that we keep using, that particles are asymptotically free. So, so our assumption, let me just write it, assumption. But I'll write it in, I'll slightly contextualize it now. Outside mod x prime equal to L, we are assuming that x mu a sigma a is p mu a plus b mu a sigma a. But of course, this is strictly speaking not correct, however far you go, because there is gravity between particles, right? So we have to estimate the error we have made in assuming that the asymptotic trajectory is free at S sigma a, at large sigma a. Is the statement clear? That we have assumed that if you go to early or late sigma a, then this is the trajectory. But this is, of course, strictly speaking not true, because there is always gravity, right? So we have made some error and we want to estimate the error. So let's estimate the error, and if the error is subleading, then our results are correct. Okay, that's the statement. And let's see how it goes. So this is my, again, let me say, this is my picture. This is mod x prime equal to L. And I have some particles which are moving out like this. So you notice that the force between these particles, so if you say particle A and particle B, and I'm writing now this schematically, the force between the particle will scale as 1 over L to the d minus 2. Right? Because they are at least distance L away. Which means that if I'm ignoring this force between these two particles, I'm ignoring the change in the velocity, which is, so that means that delta V, correction to my velocity, will be of the order 1 over L to the d minus 3. Is this clear? Because I integrated once. Is this part clear? Because this is acceleration, and to get the velocity, I have to integrate once, right? So I get 1 power more in the. But that would mean the change in the position as compared to the free trajectory will. So the error we have committed by assuming the trajectory is free is of the order, because I integrate velocity once. Is this part clear? So, because L is the distance, at least the distance when they are outside the radius L. It's like 1 by r square for 4D. Spatial distance. which is at least L. So we are assuming that you have particles which are moving freely. We are estimating the correction that we would have to make. So I have free particles. Okay? The distance is L. Understand? And so at least the error we have made is this much. I mean, the force we have ignored is of this magnitude, which means the correction to the free V would be of this magnitude and correction to the trajectory would be of this magnitude. But if D is greater than 4, and as you take L large, this term is 0. So for D greater than 4, as L becomes larger, delta X mu A vanishes. So our assumption is safe as long as D is not 4. So you may think that everything we did is a waste of time because we are in 4 dimensions. But this analysis taught us what is robust in above 4 dimensions and what we'll have to change in the 4 dimensions, right? So is this part clear, by the way? So let me give an illustration if this is too abstract. So that is why what we have done is correct, because our assumption is correct as long as D is larger than 4. And our assumption is completely break down if D becomes equal to 4. And that Ashok will now do actually do the D equal to 4 case from tomorrow. So he will do whatever theorem we did, he will actually do it for 4 dimension. And this is the part that he will have to, he will take care of. So let me now tell you if this is confusing what exactly we are telling. I think this will make it very, very clear. So let's just look at Newtonian gravity. And so, let's take let's just write down the usual. And let us say that I wanted to estimate the trajectory at asymptotic time. As mod t goes to very large, then I can solve this trajectory. And you can imagine that if I start with a free trajectory, if I start with x equal to, just for simplicity, I'm taking no a plus vt, just vt. Then you see that if at late time you assume first this trajectory, then and you solve this equation, then this equation would become there should be x hat of course here. Dt square is gmm by mod v square t square x hat. And so now if you see like what is the correction, so you want to solve this equation, so you have to integrate twice, and then you see that the corrected trajectory, so the first you are assuming first it's free, then you are asking, okay, at late time what is the correction? And the correction you can see is of the form because if d2x by dt2 is 1 by t square, then x has to have a log behavior. So even in Newtonian gravity, you see because of the long range force, however late time you go, the trajectory is never free because this term is not dying, right? And this is the term we have assumed is not there, which is why our assumption is same as saying that we are in higher than 4 dimensions. Is this part clear? So you could imagine that many things will modify once we start considering this correction to the trajectory. This is indeed a correction because this term is smaller than this term, because at large t grows faster than log, but it is not a term which is decaying in t. That's what we have missed. So it's not like we have missed a term which is more dominant than free trajectory. Obviously, that will be crazy because we are not dealing with quarks. But it is certainly something we cannot just drop. So that's the subtlety that Ashok will deal with from lecture 3. And he will generalize the soft theorem in higher 4 dimension. So any questions so far? Yeah. Say that again. So this is let's just go as this is 1 by r square. And then if you integrate once, it will be 1 by r. Yes. And so that is correct, no? If you are in 4 dimension, this is 1 by r. And then if you integrate one more, this will tell you that it goes as log. I mean, d minus 4 is log in 4 at equal to 4, right? So Yeah, and that we see it explicitly now in this simple case. So it's not a question of even relativistic theory. I mean, this is true even in Newtonian gravity. If you have done quantum mechanics course in scattering theory, you would know that they always avoid defining scattering matrix for Coulomb potential. Because this is the reason, because particles are never free when you have 1/r potential. Okay, so that basically finishes my oh no, I have to tell you what the nonlinear part is. Then that will finish the classical stuff. So far this is the result. Oh, where is it? Oh, we deleted it. We have the result for the particle case. Now we are going to write the stuff that we dropped. And the analysis follows exactly like in the particle case. In fact, you could think that gravitational field is like massless particles. But you could also actually take the stress tensor of gravity and do this computation. I will give you the reference in the end. And there's nothing conceptually different, but it's just a horribly messy computation. But in the end, the contribution from the nonlinear piece up to order omega to the 0 has the form integral over plus oh, do not cross. I already crossed. Thank you. Oh, it should be symmetrization, of course. And then we have I will explain the notation in a minute. J graph omega. Sorry, I'll just delete this. New lambda omega, a lambda divided by E graph. So you can explicitly prove this, that the contribution from the gravity is given by the and there should be I here, where P graph omega is the linear momentum flux of gravity at angular location omega. So you integrate the full linear momentum of gravity, the flux of gravity, but at an angle omega. That's what this P mu omega is. It's not the full linear momentum of gravitational field. For that you have to integrate over omega. But this is just the density, momentum density of the gravitational field. Similarly, this is the Poynting flux, the angular momentum of the gravitational field, but at an angle omega. Is this clear? So the result is exactly structurally the same, except that instead of sum, we have an integral. Because yeah. Okay, so that's and the way to prove it is to do the same thing we did, except you have to take into account T mu contribution from the fields, gravitational fields, or whatever other massless fields you may have. I wrote here P gravity, but if you have electromagnetic fields also, then you will have contribution also from electromagnetic fields. So whatever massless fields you have, they will all contribute. Their linear momentum will contribute to the leading term, and their linear and angular momentum contribute to the subleading term. But the result is universal because that the structure is independent of the theory, or the details of the scattering. Okay, so that basically finishes the. Let me just write the main punchline, and then how much time, Ajith? Okay, maybe I give you a brief. Either we can do questions, or I can give you a brief sketch of the quantum. I mean, one just you can always imagine, right? That let me write something. So let's look at let's do the following. Evaluate the following quantity. So this quantity is same as No, that's it. Is this clear why? Because if I multiply with omega and take omega to 0, the subleading term drops out, right? Because it was omega to 0. Similarly, if you do this limit, plus the nonlinear term, I will not write it, nonlinear term. By nonlinear term, I mean this term, huh? This term. And if you do this limit instead of this limit, then of course you can imagine the 1 by omega term drops out, but the omega to the 0 term survives, and that will give us exactly the remaining the thing that we wrote earlier. Okay, is this clear? Plus the nonlinear term. Now, you can notice that this should remind you of something. The fact that this is completely independent of any theory we are looking at should remind you of the fact that it's very reminiscent of some conservation, because it is telling you that the gravitational field at infinity to leading order in soft expansion equal to something. Similarly, to next order in soft expansion equal to something. And it should remind you of if you did these two equations should remind you of something, which is the following. Not remind you as some quantitative thing, but as a as a parallel that in any scattering, in any classical scattering, it can involve gravity, not involve gravity, whatever it can be, but we know that total incoming momentum is always equal to total outgoing momentum. And similarly, total ingoing angular momentum is equal to total outgoing angular. Right? But there are two statements about this. One is that we know that this object is related to existence of symmetry. So we know this is true for any theory in any scattering in Minkowski spacetime, because of the fact that we have, both are true because of Poincare invariance. So one thing immediately we should realize is that means that the fact that these are, the fact that this is always true for any scattering in approximately Minkowski space means that there must be some symmetry underlying these two statements. But if there is a symmetry underlying these two statements, then they should also have a parallel in quantum theory, because of the fact that we know that in the end, classical physics emerges out of quantum mechanics, and the fact that classical scattering satisfies this really comes from the fact that quantum S-matrix satisfies conservation of linear and angular momentum. Is this statement clear? Which means that these two statements must have a parallel or their origin in quantum theory. Right? So it should be true that in quantum gravity, such something should be true, such that when we take classical limit of quantum gravity, we get this. Is the connection clear? And indeed, this turns out to be true. So I will just write that summary of where, if you don't believe in classical theory but always want to go from quantum, what result in quantum mechanics whose classical limit will produce this these two results. So can I erase this? Okay, so the idea is that because these are universal results, they can't be standalone results in classical theory, right? They must have something to do in quantum theory. I mean, in general, you could have some results in classical theory coming from some decoherence effects, which are not manifest in quantum theory, but results which are completely theory independent, usually we expect that they must have their origin in quantum theory. And right now, because we are talking about gravity, they must have their origin in quantum gravity. So it is indeed true that in any theory of quantum gravity, so we don't need to know what quantum gravity is. It can be any theory. but it should satisfy some properties, which is not always true. So I will write what assumption it has to satisfy, which admits flat space as a solution, as a state, let's say. So in any theory of quantum gravity, if you scatter any quantum states, so you take some, I'll just do it schematically. So you take any states, but when we study scattering, we can always think that states are localized. So I'm just drawing them like classical particles, but they are really states with incoming momenta P1 to Pn, the same thing, except now they are all quantum particles, and outgoing momenta P1 prime to Pn prime. I think Jan discussed a little bit introduction to scattering. We can ask what is the amplitude, probability amplitude for the m incoming momenta to go into n outgoing momenta, and let's say L gravitons with momenta k1 to kn. So of course, it looks impossible because to actually compute in any theory of quantum gravity, we have to know the theory. And so how we can say anything about this just by assuming that the theory has a Minkowski vacuum as a state, and the theory is generally covariant, like just by assuming these two things. So it turns out that this has a remarkable answer, which is true in string theory or any theory, which is well, actually only string theory, because that's the only theory of quantum gravity which admits flat space as a solution. So in string theory, or if you don't want to talk about string theory, in quantum gravity, this amplitude, if you take this case to be soft, which means that you take their energies to be much smaller than the energies of the other particles, then this amplitude has an expansion, which is universal, and that expansion is the following. So this is a really striking fact, and then I'll tell you why it's related to what we derived. Product. It's a slightly lengthy expression, so I will just write it. Godwin, you tell me if it shrinks too much. That's the first term. So here Ki is the momentum of the ith graviton, and epsilon is a polarization tensor. So graviton is same as linearized gravitational fields. If you don't, if you have not studied, it's not a problem. Just think of it as a linearized gravitational field in momentum space. So the fact, if you take soft expansion, you get first term which is like this, which is product over all these factors. And you notice the parallel, right? This is exactly the factor that we derived in classical theory. So already you start seeing some connection. Plus, you get several terms, which is, now I have to write a slightly lengthy final expression. It's always good to write last equation as long equation, so that from tomorrow you are happy that I am not around. So it's good to write the ugliest equation in the end. So I'm going to call this object, just because I don't want to write it again and again, as a soft factor which depends on the ith graviton. Okay, so is this clear? That notation is clear. This entire object, including the sum, I'm calling it like this. then J mu nu plus, okay, I'm going to write it like this, plus a term which I'm just going to write it as a, so both these terms, you notice there is something interesting. In this term, you just have product over all the gravitons. In this term, you have product over all the gravitons except one of them, and then there is this factor here, which also has a parallel with the subleading soft factor we derived. And then there is a term which is complicated, I won't write it, but it is something that involves pairwise. So it is sum over all I less than j from 1 to L, some term which I just call Mij. And it will depend, of course, on all the momenta of the particle, other particles, Pa. So this giant factor, the probability amplitude that you have m incoming particles, quantum particles, they scatter into n outgoing quantum particles. These particles, they don't have to be same; they can have different species, etc. Plus L soft gravitons. In the soft expansion, we get these terms multiplied with the amplitude without the gravitons. P1 to Pn. This result, which is a striking result, remains true as long as you are. So of course, this result depends on one thing, and that thing is that the S matrix is well defined. This amplitude is well defined. So if the amplitude is well defined, it means it shouldn't be zero. If the amplitude is not zero, then you have this statement in any theory of quantum gravity. And let's look at the orders. So you see that this has L of this case. So if I think that all of them are having frequency omega, the first term goes as 1 by omega to the L, right? Sorry, this L is not, I don't know why I use this L. This L is not the radius L, this is just the number of gravitons. This term you notice, this has product over L minus 1 of these S zeros, and this one is order omega to the 0. So this factor goes as 1 by omega to the L minus 1. And this I didn't write down, but it turns out this factor is also of order omega to the L minus 1. And of course, then what are the terms I have suppressed? The terms I have suppressed are of the order L minus 2, right? Those terms I have not written because we don't know much about these terms. So in any theory of quantum gravity, these terms will depend on the details of the quantum gravity theory. But up to this order, this is a statement that was pioneered by Ashok, this proof, and then it was proved in full generality by Ashok, Subronil, Vishwajit, and Mrityunjay in 2019. So this is a rather remarkable statement, and you see that why, if you didn't know anything about classical soft theorem and you knew this, you should know that, oh, then something should come out in classical theory, because some universality about quantum gravity amplitude. Is this clear what we are saying? Okay, now I'll finish in 1 minute how we can connect from this to the thing we derived. The details will be given in the tutorial. No, in the, it was already given. Oh, you will give today. So some details of how to connect, you give into a tutorial, but I will just tell you the rough idea. Just very basic idea. The idea is the following, that let's look at the following process, that you have some very large objects, classical objects like black holes, etc., and they are scattering. But of course, every classical object can be thought of as a semi-classical quantum state, as a quantum particle with minimal uncertainty. So think of them as large objects which we want to describe using quantum wave function, like, using the minimal uncertainty wave function. And now you can ask, if I have a detector, say a place somewhere, which has an angular separation delta omega, and the frequency resolution omega plus delta omega, where omega is much softer than all the all the momenta in the problem. Now you ask the following question. We know this result. We can ask the question, what is the probability if you take a detector which is only detecting very soft radiation, what is the probability that you get n gravitons? So let me write it in textual form first. So we can compute a conditional probability, and then we can do classical limit by extremizing the probability like we do usually. So what is the probability that n soft gravitons are detected by this detector, detector which has an angular resolution this and frequency resolution this. Now, when the scattering is happening by rules of quantum gravity, so we don't know anything about this scattering. So this is some, I call it A, quantum gravity. So given the fact that you have some theory of quantum gravity which is dictating how these objects are interacting, what is the probability that you can detect n gravitons in a specific detector? So you find that n, and the reason you can find this n is because of the theorem we wrote down, and then you extremize n. So when you extremize n, you find an answer which is such that so you will find some n extrema. These details will be given in the tutorials. I am just giving you a picture, such that if you write down the total energy, so the total energy in the gravitons, because they are all in this frequency range of omega plus delta omega, is of the order of this one. And now you can check that if you took our radiative h mu nu up to subleading order and you computed the energy from it, then it will exactly match the result that you find. So that's the first connection that you make between the result we found and a result in quantum gravity that whose classical limit in this sense gives us what result we found. Is the statement really clear? We computed a radiation field, but from there we can compute its energy, and that energy would match with the energy that you would find from this procedure, where you find the extrema of the number of gravitons that are detected in this graviton. Okay, I'm just about done, so maybe I can take questions. Yes. Yeah. Yeah, you can use them. Yeah.
So can I replace the H mu nu with the electric field and do soft photons and get the same result?
Yeah, but the thing with photon is that it has a parallel. It's a very good question. That if you do the same thing with electromagnetism, then the leading term you get is indeed universal in the sense it's independent of the details of the theory and also details of the the multiple moments of the scattering objects. But the subleading term is not quite universal, exactly like the subleading term in gravity. So it has that piece from just if you take normal minimal coupling of some charged particle with electromagnetism, it will have a particular piece plus depending on the coupling extra terms. And if you go to the order omega, then we can't say anything, there is no theorem. So like in gravity at omega squared, there is no theorem. So there is indeed a parallel. Yeah.
And also one last question that was regarding the fact that we took Minkowski spacetime as background.
Well, it's not a background, it's just asymptotically Minkowski.
Yeah,
so inside we are agnostic. We don't know, it could form black hole, it could do so many things. We never assume anything about the geometry in the interior, of course.
The symmetry that we were using was the asymptotic symmetry of...
Yeah, I mean, I didn't discuss it, but indeed it is a fact that I was drawing parallel is the fact that there are indeed symmetries whose conservation law gives us these soft theorems, which as you know, BMS and this thing, but we didn't have time to, yeah.
So this won't be true for asymptotically ADS or DS? spacetimes because I won't.
Yeah,
have quantum
not as, because in ADS, for example, you don't have soft graviton because ADS is like a box. So every graviton has a maximum wavelength, which is the size of ADS. But it doesn't mean you cannot do some kind of a soft gymnastics, people do, but it will have different physics than this, what we did here.
Are there any further questions? So if not, Alok will be.
Tomorrow Ashok will be there, say
Yeah,
answer all your
he's already here. So, I wanted to thank Alok for giving this very lucid set of 2 lectures, and we are particularly grateful because he had to step in at short notice. Thank you very much, Alok.